So I looked at 4 of your homework questions that I thought were representative or particularly significant. The first one was the one about mammals and warm-blooded creatures. And we talked about that a little bit on Friday. The first part was asking you to, so you had propositions M of x says x is a mammal, W of x says W is warm-blooded, and A of x, I think, said x is an animal. And you were asked to write the statement that all mammals are warm-blooded. And this is a little bit of rewording. All mammals are warm-blooded. So mammals are warm-blooded. That's really a conditional statement in some sense. It's saying that if something is a mammal, then it is warm-blooded, right? So if X is a mammal, then X is warm-blooded. And it's saying this is true for all X that are mammals. Right. So this part in here, if X is a mammal, then X is warm-blooded, is really a conditional. Mammal X implies warm-blooded X. And then the all in the beginning there is basically saying for all X, this conditional is true. So for all X, if X is a mammal, then X is warm-blooded. Does everybody see where that gets you the same thing as saying all mammals are warm-blooded? On the other hand, if you do something like this, that says something different. That says for all X, X is a mammal and X is warm-blooded. It's saying that the only things in your universe are warm-blooded mammals. And that's a more powerful statement than this, because this says, there might be mammals, there might be fish, there might be plants. But if X is a mammal, it's warm-blooded. This is saying anything that you pick out of the universe is a mammal and it's warm-blooded. It's a very different statement. It's more powerful. So it's tricky sometimes going between, particularly from English to a statement like this. But that's what these exercises are for, right? Get some practice with that. And when I assign exercises in the book, by the way, those are just sort of representative ones, but there's usually more questions like those in the book, including the odd-numbered questions, which have solutions in the back. So you're encouraged to look at the other questions as well and think about them or try to make up some of your own. Right, work with the concepts. The other part of 2 was going in the other direction, starting with propositional logic and trying to turn that into English. And that's a little bit easier because the propositional logic should be very precise. So there exists an X such that A of X and not M of X. And this is really saying there exists an X which is an animal and is not a mammal. So more normal sounding English, there is an animal that is not a mammal. Because we don't usually say there exists an X such that X is a new restaurant I want to try sometime. We just say there's a new restaurant I want to try sometime.
So should we avoid the use of X?
So these questions are a little vague, but if you're asked to convert something into English, it should sound, I guess, like normal spoken English, right? I mean, I could convert this into English by saying, there exists an X such that A of X and not M of X. Technically, I converted it to English, okay, but that's not the spirit of the question, which wasn't necessarily clear. The spirit is to find something like this, right? Just sort of a plain sentence that corresponds to that. And there may not always be a precisely clear, meaning what that pathway is, what exactly that sentence should look like. It's really exercises in sort of thinking about everyday speaking versus propositional logic, sort of what are the bridges there between them. That's more the main point of it. All right, question 6 was showing that for every integer there is an integer bigger than that, positive integers. And we talked about this one Friday also. For all x, there exists a y. Let me be precise. For all x contained in, let's use this for the positive numbers. For all positive x, there exists a y also in the positive numbers such that y is bigger than x. So for any x that you think of, I can find some y that's bigger than it. And here again, some people said there exists a y such that y equals x plus 1. Well, that's a much stronger statement too. That's not saying just that there's a number bigger than x. It's saying that there's a number 1 bigger than x. Right? Now this is certainly something bigger than x, but we weren't asked to show that there's a consecutive integer, right, which is one more than any integer. We were just asked to show that there was an integer bigger than x. And so all you need is y is bigger than x. So this one, not really. Let me show you something else I saw. For all x, there exists a y such that x plus 1. So without knowing anything about what the question was asking, what can we immediately say is wrong with this?
It quantifies the y, but then it doesn't use the y.
It doesn't use the y, although that's not necessarily a problem, but it's certainly a suspicion that there's something going wrong here.
X plus 1 isn't a proposition.
Exactly. X plus 1 is not a proposition. And so for all x, there exists a y such that not a proposition. This whole thing, it fails to be a proposition. It's actually a mix of quantifiers with something that is just an arithmetic expression. So that doesn't even have meaning in a strictly rigorous sense. And we're going to see this when we talk about the proof in a second. So number 10, we also talked about show that there's always a solution to a plus x equals b. So for all a, I don't know if this was reals, I'm guessing it was. For all a in the reals and for all b in the reals, there exists an x such that a plus x equals b. And most people got pretty close to that, if not exact.
Quick question.
Yeah.
So when are we supposed to and not supposed to use like the universe subscript?
I'm using it here only because I'm writing it and it's being recorded. I get pretty sloppy with it. If it's clear what the universe is, you can leave it off. But it's got to be clear somehow what the universe is. So I might say something, where a and b are real numbers, and then for all a, for all b. It doesn't hurt to put it in. It just makes it a little longer. But you're not going to go wrong by putting it in. But if you're doing a proof that's 20 lines, you can say in the beginning, a and b are contained in R, and then just go from that. All right, so let's talk about this proof. So prove if a divides x and a divides y, then a divides, I don't remember what it was, but let's just do 3x plus 5y. And the specific numbers aren't really important. And we showed this last week, but let's go through it again. Let me point out some things to watch out for. So I would clearly say the word proof when you're going to start your proof, because in some cases people wrote 2 or 3 versions of this and then just started in with their proof, and it's not clear where the statement of the question ends and the proof begins. And if I write down something like a divides 3x plus 5y right here, and I think that's part of the proof, that's a problem. So, draw a line or something to indicate where your proof begins. And number your statements, just because, but also so you can refer to them. And our first statement might be a divides x. That's a premise, that's given. That's a hypothesis. There's different ways to phrase that. All right, if a divides x, we can also say x is a multiple of a. Or there is some integer c such that x equals a times c. So there exists some, let me just stick with k because we always use k. There exists some integer k such that x equals a times k. And that's the definition of this divide symbol. And this is really what we're looking for. We want to write x as a multiple of a. So we can write 3x plus 5y as a multiple of a. And pretty much everybody who did the homework, I think, knew where we were trying to get to, right? We were trying to use this divisibility to rewrite x and y as a times something and then just pull an a out of this parenthesized expression. And we get our answer. But it's about how you formalize it. Alright, so a divides y, so there exists a j in z, such that x equals a times j. And nobody used the same k for both of these, which was awesome. That's usually a long battle. So everybody got that. Alright, so now we got to be careful. And let me show you something that I saw in some cases that is actually a problem. So in some cases, I saw this. 1, a divides x implies x equals a times k. K is an integer. That is a proposition, and it is a true proposition. But it does not help us in this proof. Because now if you try to do something like 3x equals 3 times a times k, that does not follow from anything in your proof, because we did not state that x was equal to a times k. We stated that if a divides x, x is equal to a times k. But we don't know that x equals a times k unless you subsequently say a divides x, and then use direct reasoning and put those together and say x equals a times k. You gotta have this somewhere before you can say 3x is equal to 3 times ak. You see what the difference is there? It's really subtle. Right? This is a true proposition, but what we're really after is this proposition. X equals ak if we're going to substitute it. So it doesn't do any harm to write propositions that you don't use, but make sure that everything you write down follows from a proposition you've already written. And this is a y. Alright, so we've shown x equals a times some k, y equals a times some j, and now we can just say 3x plus 5y equals 3 times ak plus 5 times aj, and we can keep going with the algebra. Equals a times 3k plus 5j, and that's substitution and other algebra. And once you've got this 3x plus 5y equals a times some integer, okay, most people noted this, which is a good idea. This is an integer. And now we can say a divides 3x plus 5y. And that follows from 5, 6, and the definition of divides. And then you say we're done with the proof. And make sure everything you write is a proposition. Right, if I just write 3x plus 5y, my proof is no longer a proof because I didn't write a proposition here, I wrote an expression. If I say 3x plus 5y equals something, that's a proposition. That's a good step in a proof. This is an integer, this divides that, this divides that. There exists something such that this equals that. Those are all declarative statements. So there's definitely some proof questions on the midterm. So be really sure that you know how to do something like this and ask questions right now if possible, if there's some confusion about what you can or can't write here or why you write certain things. Alright, so let's peek at the midterm study guide. So this is really just kind of a synopsis of what we've been doing so far. Mostly set theory and logic and a little bit of number theory. So let me start with the end. Number theory. I want you to know about primes, just the basic things we've talked about. I want you to understand modular arithmetic. And I want you to know how to use Euclid's algorithm to find the greatest common divisor. In fact, I'll tell you right now you have a question on that. Okay, I'll give you two numbers, ask you to find the GCD. I will not ask you about modular exponentiation. I will not ask you about Fermat's Little theorem. So the stuff we've been doing the past day or two and the applications we started talking about will not be on the midterm. Okay, but modular arithmetic, is this number congruent to what? Modulo such and such. You should know. And how to find a GCD. When you find a GCD, make sure you're showing all your work. If you get the right answer but there's no work there, you don't get credit for it. So you got to show me how you're going through step by step. All right, so let's just go backwards. So proofs, direct and indirect proofs. Indirect proofs are proofs by contradiction. So you should be able to do either of those. And in particular, proofs about even and odd numbers. So proving theorems about even and odd numbers. And I may say without using modular arithmetic. So like show that the product of two even numbers is even. Well, that's easy if you just work mod 2. Both numbers are congruent to 0, their product is congruent to 0, so it's even. But if I want you to do a proof of this without using modular arithmetic, that means using the definition, number 1 is even, so it's twice an integer. Number 2 is even, so it's twice another integer. Multiply those out, it's 4 times another integer, which is 2 times some integer, which is even. So we've done these. You had homework doing 4 or 5 of those. But again, the structure of the proof is really the most important part on these kinds of questions. The thing you're trying to prove is usually something that's pretty self-obvious. It's really about how you put together the steps of a proof. So being able to make that very formal, rigorous argument, that's what we're after.
So we get to bring in that purple page with the list of blocks.
Yeah, you can bring in the purple page. That does not count against your page budget. All right, so propositional logic in general. What is a proposition? Declarative statement that has a truth value. Writing propositions, deriving new propositions from old. So we can negate, we can take an and, we can take an or. These all give us new propositions. We can do implications, if P then Q, or the double arrow, the double-headed arrow, if P then Q, and if Q then P, which is also P if and only if Q. Truth tables, you should know how to write a truth table. That's good old 250 stuff. Make sure you know what the converse and the inverse and the contrapositive are. It's worth points. Okay. Inverse of P, so here's a statement. Converse flips them around. Inverse just negates them. Contrapositive does both. Okay, if it's Monday, then we have class. If we have class, then it's Monday. If it's not Monday, then we do not have class, right? And these are different statements from the original. But if we do not have class, then it is not Monday. That's the same as the original statement logically. If it's Monday, we have class. If we do not have class, therefore it is not Monday. Those have the same logic values. So a conditional and its contrapositive are logically equivalent. Converse and inverse could be different. And inverse, I just think of inverse as like taking a not operation, so it's the one with the nots in it. Propositional equivalence, which is when two propositions have the same truth values in all cases, and one way to show equivalence is by showing a truth table. And if everything in one column matches everything in another column, those two columns have the same truth values in all cases, they're logically equivalent, propositionally equivalent. You don't need to memorize a million identities, but you should know most of those identities just from working with stuff. For example, P and Q is the same as Q and P. There's commutativity, there's associativity, we can distribute, there's De Morgan's theorem, and I'm not going to ask you to name those, but you should know them. They're also on that sheet, that blue sheet. But you should be familiar with those because they're useful. Most of us know those well enough we don't even think about it. We flip around the order of things if it's convenient and we don't realize that there's anything going on, so not too much to worry about there. Proving propositional equivalence using identities. So if we don't use a truth table, we can use some of these identities to manipulate one proposition into another proposition by distributing, by simplifying, things like that. And most of that is analogous to stuff from 250, Engineering 250. Quantifiers we just did, so if I ask you anything on that, they're not going to be very heavy, but for all, and there exists unique, and nesting of quantifiers. Rules of inference will definitely be on there. That's how we prove these things. So direct reasoning, indirect reasoning, disjunctive, simplification, and all that other stuff. Proving an argument is valid, so when you have something like some expression on the left, maybe with commas in between, saying all of these things are true, and then the double-lined arrow, right, that means that everything on the left implies the thing on the right. And so if you have something in the form A, comma, B, comma, C implies X, it basically means given A and B and C, we can conclude X. It's just a one-line version of writing out this statement. And so to prove it, you do it the same way you would prove this. You can assume A, B, and C, you argue logically, and you try to come up with X. And then fallacies, there's two fallacies, fallacy of denying the hypothesis, fallacy of affirming the conclusion. Denying the hypothesis is like this. P implies Q, so this is a hypothesis conclusion. If we deny the hypothesis, we can try to conclude not Q. That's not correct. If it's Monday, we have class. It's not Monday, therefore we don't have class. It's not logically correct. So that's denying the hypothesis. And then affirming the conclusion. If it's Monday, we have class, therefore it's Monday. That's not logically correct. So that's affirming the conclusion. So those are your two fallacies, and they're kind of the contrast to direct reasoning and indirect reasoning. All right, and then we started off the course talking about set theory. So you did some of this on a quiz, and you've done homeworks on these. So set operations: union, intersection, complement, and complement in the universe. The universal set has everything. The empty set has nothing. Subsets: power set is the collection of all subsets. Set membership: that's the curled E symbol. The epsilon says something belongs to the set. Set builder notation: the set of all x such that x is bigger than 9 is one way to represent sets. Cartesian product, which gives us a set of tuples. The Cartesian product of A with B would be the set of tuples parentheses A comma B, where little a comes from A and little b comes from B. Venn diagrams we've done and drawn. It's just a graphical way of representing some of these operations. Make sure you know how to do summations. Make sure you know how to do double summations. Okay, if you have a double summation question, sum from I equals 1 to 5, or the sum from j equals negative 10 to 10 of something, right? Break it up. Figure out what this is first. And you'll get an expression, and it'll probably involve an I, but it won't involve a j because the j's get replaced, right? So evaluate this for each of those j's, add them together. It gives you some expression here. Now it's just a sum from I equals 1 to 5 of whatever that expression is. So just work through it piece by piece. Membership tables are basically truth tables, but your ones mean that an element belongs to a set. 0 means it doesn't. But if you use that kind of notation, then when you take the and of two things, it works like a logical and. It works like an intersection. Something's in the intersection of two sets if it's in the first set and it's in the second. Something's in the union if it's in the first set or it's in the second. Theorems about sets, same thing that we have for propositional logic. There's commutativity, associativity, distribution, De Morgan's theorem, and so on and so forth. And so, again, we can prove various identities either using membership tables, truth tables, or by using these theorems and identities. So set theory, a lot of what we did really just kind of set up a framework that we would revisit in propositional logic. But you can understand almost everything through set theory. So questions about any of that? So we'll take like an hour for the exam, and then we'll lecture afterwards. But I'll probably start a few minutes after 12:30 to give people time to come in a few minutes late. And then we'll go ahead and do the exam, take a break, and then do a bit of lecture afterwards. All right. Have we talked about Principia Mathematica? Sounds like a fun book, right? So Whitehead and Russell, Principia Mathematica. This is volume 1. $45 for the set of 3 volumes. That's a bargain. I don't think you can get it for that anymore. This was an attempt by Whitehead and Russell to take mathematics and make it very formal. And we think mathematics is pretty formal anyway, right? But we played with Russell's paradox a while ago, where we had sets that contained themselves, and we saw that once we allow that definition, we were able to create a paradox where we asked a question and it could be neither said to be true nor false, because each led to a contradiction. So Whitehead and Russell set out trying to come up with a better way to describe mathematics. Kind of like has been done with set theory, right? Trying to put it on a very rigorous footing. And so this was done, I believe, yeah, first edition 1910, right? And the preface is worth reading because it's written in English, unlike most of the rest of the book, which was written in its own language. Let me find you a good section here. This is still just introduction. Let's jump into the guts of it. So it's stuff like this. If phi of x always implies psi of x, then phi x always implies psi x always. That's a theorem, and here's a demonstration or proof of it. And this is meaningful to Whitehead and Russell. It's a different language, right? So, you know, when we use English or any written language, we sort of introduce ambiguities and opportunity to go astray. So this was trying to be extremely rigorous. And this goes on and on and on for like several hundred pages. And I don't know who proofread this, if anybody. Theory of propositions containing one apparent variable. So, yeah. So this was a grand project, right? To make mathematics very formal and make sure there were no more of these unfortunate paradoxes popping up. And I'll show you one page in particular that's noteworthy. So here's some more stuff that I guess looks good. There's a footnote down here at the bottom. This proposition is used in 163. Oh no, that's not the right one. Here we go. Okay, so here's a proposition, right? I don't know what that says, but it says from this proposition it will follow when arithmetical addition has been defined that 1 + 1 = 2. Okay, and this is on page 379. Okay, so this was a heavy project, and they finished it and they published it and it was pretty good. And then it all kind of went out the window in 1939 when somebody showed that that you really can't do what they were trying to do. And if you come to your Canvas homepage, the cover shot for CSE 215 is a picture of these two people. So you know who the person on the right is?
Einstein.
Einstein, right? He's easily recognizable. The person on the left, his name was Kurt Gödel, G-O-E-D-L, G-O-D-E-L. And he proved in 1939 that like this mission to make arithmetic perfectly consistent and complete was impossible. He showed that you can't do that. You're either going to have paradoxes or you're going to have things that you can neither prove nor disprove, incompleteness. And there is no sweet spot in the middle. You're either too much or too little. And he wrote a paper on it. He was a pretty much unknown figure in the community, and he presented this paper at a small conference, and most people had no idea what was about to happen. But a few people had actually read the paper in the proceedings ahead of time and were like, oh boy, this is going to be interesting. He gave his talk, and slowly it started to settle into people's brain what was going on, and they looked at his work and, you know, assumed there would be mistakes while his work was solid. And he came up with this amazing result called the Incompleteness Theorem, that, you know, you either have paradoxes like Russell's paradox, or you start getting rid of things so that you have no paradoxes, no contradictions, and as soon as you've done that, you've got things that you can't prove and you can't disprove. You've got incompleteness. And that's interesting from a philosophy point of view, what that says about human limitations. But a lot of this comes out of set theory. So I won't ask you to prove that on the midterm.
Yeah.
Yeah. Save it for the final. All right. So any other questions about exam and such?
Still have 4 pages of notes.
Yeah, 4 pages, double-sided notes, plus your purple sheet if you want it. All right, well, let's talk about applications. So we talked about parity at length on Friday, and we were looking at old modems and error-correcting codes. And that can lead us to talking about something called hashes. And I tried to find a disgusting picture of hash, and all the pictures I found actually made me hungry. I'm vegetarian, but that still makes me really hungry. We'll talk about hashes in 222 at length, CSE 222. But here's the basic idea of a hash. You have some large universe of stuff. Could be names, could be pictures, could be whatever, right? Just some collection of things. And we want to map this into some small universe of integers, modulo
We can't see.
some number. Oh, that's such a cool picture. All right, we have some collection of stuff, names, pictures, something like that, and we want to map these things into some small collection of integers. And we're thinking of integers modulo n, so it would be integers like 0, 1, 2, up to and including n minus 1. And we do this mapping with a function called a hash function. So what's an example? Suppose you take somebody's name and you take the ASCII code of each character and you add all those ASCII codes together and you get a big integer and you reduce that modulo 99. Okay, that's going to give you a number between 0 and 98. That's a map from this space of all these different names into a set of 99 unique integers. Or we could take a JPEG file, and we could take each byte of that JPEG and multiply it by the position of that byte in the JPEG file, and add all of those together, and take that and reduce it modulo 2 to the 32nd, so we get a 4-byte number. And then we could take those 4 bytes and we could add them together as 4 single-byte numbers and reduce that modulo 256. And now we've got every picture mapping to a number between 0 and 255. So hash functions can be weird, random, crazy things, right? They usually involve arithmetic operations and some kind of modulo operation. And the end result is we have a mapping from things into a small set of integers. Okay, why do we want a hash function? Because once we have an association between, say, names or pictures and a small set of integers, we can use those integers to store those things in an array and make it really easy and efficient to find them later. So suppose we take a series of JPEG images and we map them to numbers between, say, 0 and 99. And so in each of these locations in this array, 100 elements, we store, I don't know, some sort of reference to that picture. Okay, now we can say, do we have such and such a picture in our database? Well, we take the picture we're looking for, we compute what the value of the hash function gives us, and we just look in our table. And we say, oh yeah, there it is right there, or this table spot is empty, we don't have this in our database. So hashes are a really efficient way to sort of store things and retrieve them, usually with a single operation, ideally.
I'm not sure I understand how that would work. If you have something in that big stuff thing, not just this is kind of a many to one function.
Yes.
So if you have, if
So
we have-
ideally, it's a
if we have
one-to-one.
all the people in this room
Mm-hmm.
map to some number in the 0 to 99, and suppose we all map to 7,
Yes.
then how?
Then it doesn't work so well. But if everybody maps to a unique number, it works perfectly, right?
Right.
Okay. So the degree to which it maps uniquely is a measure of how good your hash function was. In the ideal situation, right, everything maps uniquely. So here's a more here's a simpler, more realistic example. Maybe you have names, and maybe in our table over here we want to store your phone number, right? So 100 possible locations here. We take your name, we hash it. If it hashes to a 7, we look at location 7, and that's where your phone number is stored. And if everything maps uniquely, that works great. Because we don't have to search for your name out of 100 names. We just have to take your name, see where your phone number will be stored, go to that spot, grab your phone number. But it's...
Then I don't see how the hash function is useful if you need to retrieve a specific thing, and 99 and 150 stuff things are all.
Yes. So if you have multiple things pointing to the same integer, if your hash function takes multiple things to the same, your function is less useful. But if you've got a million names over here, and your hash function tends to bring 10 of them to the same integer, that's not too bad. You've got a name, it could be in one of 10 possible spots, right? 10 possible things could be going to that. So now you have to check 10 things to see which one is actually your name and find the phone number, but it's reducing your space. But this is the problem with hash functions. This is where they're great in theory, but in practice they're less than perfect because you get what are called collisions. Multiple things are mapping. But we have ways to deal with that. So that if two things map to the same thing, we have an algorithm for where to store the second one, since the first place is already spoken for. And if that algorithm is pretty efficient, and if you don't have too many of these collisions, like I say, if you have 10 out of a space of a million names, that's pretty efficient. Because 10 operations, worst case, you can find your name.
Is it the case that everything from stuff is stored in a unique position? It's associated, well, we all are mapped to 7.
Mm-hmm.
So we all have 7 associated with our names.
Yes, but
is each one of us stored in a specific
each one will be
individual
one will be
location?
stored in 7, and the others will be stored somewhere else. But when you go to 7 to look for somebody, there's information there that says if this is not who you're looking for, check over there, because I put someone there too. And you go there, and if that's not who you're looking for, there's something that says, oh, but check over there. And maybe when you check there, there's something that says, well, there's nobody else stored, and now you know the person's not in the table.
Okay.
And that's machinery that we'll talk about in 222 when we actually talk about hash functions and algorithms for using this. The 215 relevant part is just the idea that we can do this ultimately by using some kind of modulo function, right? If we have n spots in here, we can reduce modulo n and get, say, an index into an array. And if we find that the spot we want to store this name is already in use, we use another hash function, which gives us another location, and we reduce that modulo n, and so on. But it's similar to parity in that it's taking this large space and reducing it to something much smaller. Parity reduces a byte, say, to a 0 or a 1 as a check bit. Or it takes a string of 100 characters and reduces it to 8 bits. That's a checksum.
Could you use multiple? I mean, I'm asking because I've never.
Yeah.
I know a little bit of mathematics, but I haven't studied this before.
Cool.
Seems to me like you might be able, an idea that you might be able to use multiple hash functions,
Mm-hmm.
and the use of those multiple hash functions would tend to allow you to uniquely identify a particular. In other words, there's all of us mapped to 7 over here, but my name starts with R, so it maps to all.
Yeah. So here I'll
Does that make sense? What I'm saying?
It did. So this is optional. This is not like this is 222 now, but here's what we're going to do. We're actually going to have a hash function that takes the key that you're trying to hash, but also takes something we call a probe. It's an attempt number. So we first use the probe of 0 and we find f of your key comma 0. And that tells us where we should store your name. If that's in use, we rehash with your key comma 1. If that's in use, we rehash with key comma 2. So your hash takes two things. It takes the key you're trying to store, but also takes an attempt number. And each time we change the value of this second argument, the hash will take the same key to a different location. And we do that to keep trying different spots in this table until we find a spot that's open. And there's a bunch of cool math about how you pick these hash functions. And we don't get into that, but there's a lot of interesting research on what makes a good hash function and what minimizes the number of collisions you get and so on. For example, if you're going to do student IDs, you could say, okay, well, I'm going to have 1,000 arrays and I'm just going to hash based on the first 3 digits of your student ID. It's a really bad choice of hash function because almost everybody starts with 940. Now, if you did the last 3 digits, that's probably a better function. That's going to tend to spread things out in here more. All right, so similar to this is UPC codes, which is a misnomer because that's a universal pricing code. But UPCs. So these are the barcodes you find on pretty much everything that you buy in the store. And the laser scanner at the checkout scans this pattern of bars, and it's a coded representation of these numbers, and then it looks up the product in the database and figures out what the price is. And these numbers aren't used unless the person types the code in manually, but the bars are used. Now, depending on the pattern of these bars, we have a different number in here. Okay, so this first digit, the 8 in this case, that's a product category. Okay, just a very broad lumping of things into one of several types of products. This 5-digit code, 11571, that's unique to the manufacturer. That identifies who made the product. And the next 5 digits identifies the actual product from that manufacturer. So general category, manufacturer ID, product ID for that manufacturer. The last digit is a check digit. It's there to make sure that all the other digits are correct. So it's kind of like a parity bit. And this is really important because otherwise you could just take a marker and you could, fill in one of those bars maybe and change it into something so your TV looks like a ballpoint pen. And they ring it up and it's $1.39 and you walk out with your 40-inch TV. So to make this code harder to monkey with, right, you can't change any of these digits unless you also change the check digit as well. And it also prevents against scanning errors because the scanner is it's an optical thing. It gets dirty and stuff like that. So if it accidentally reads, say this 0 down here, if it accidentally reads that as an 8, right, it will know that there's a problem because when it calculates the checksum, it will not come up with a 9, and it'll say, hey, something's wrong, rescan. Okay, just like parity does.
So that 9 is used when you just add up all the digits of the numbers that come before the 9?
So it's a little trickier. So here's what they do for UPCs. So it's 11 digits plus a check digit. Okay, so if we think of these digits as x1, x2, up through x11, and then we think of this check digit, let's just call it x12. So you calculate the following: 3 times x1 plus x2 plus 3 times x3 plus x4 plus x10 plus 3 times x11. You calculate that sum. And you reduce it modulo 10. And so let's call this, let me call the check digit D. So D is equal to that sum modulo 10, and then if D is not equal to 0, set it equal to 10 minus D. So let's write down our UPC code: 811571 01357. So this is multiplied by 31313131313. All right, who's got a calculator and isn't afraid to use it? All right, 24 plus 1 plus 3 plus 5 plus 21 plus 1. What have you got so far? 91. All right, let's keep going. So this is 0 plus 1 plus 9 plus 5 plus 21.
91 was everything.
What?
91 was all of it, actually.
Oh, 91 was all it. Okay. All right. So that all adds up to 91. 91 mod 10 is, right, mod 10, just take the last digit. So that's congruent to 1. So D is equal to 1. That's not 0, so our actual check digit is 10 minus 1, which is a 9. And that's what the check digit should be.
What is the way you just did it, is this that the actual way?
That's the actual algorithm.
Y3, just some random.
Y3, partially because 3 is relatively prime to 10, I'm pretty sure. I don't know the ins and outs of the algorithm. What I can tell you is it will catch 100% of single digit errors. If you change any one of the digits, you will get a different checksum, different check digit. And it will catch 90% of transpositions. So instead of 57, if I type 75, I'll get a different check digit. If I type 13, if I'm supposed to type 13 and I type 31, it'll get a different check digit 90% of the time. And transpositions are a common key punch error. So if you're typing this code in by hand, right, it's easy to put in a digit that's wrong, but it's even easier to accidentally swap the order of 2 digits. You see me do this all the time when I write code. And this should catch 90% of those errors. And the straight sum would not catch transpositions, right? If you just added these up and reduced, the order in which you add them doesn't matter. Well, here, if you swap x3 and x4, it's the difference of 3x3 plus x4 versus x3 plus 3x4. And I think that's the answer to Y3, because if you do that for different pairs of integers, I think you'll see that most of the time it makes a difference. And that's the relative primeness kicking in.
So could you say that again? Okay, I understand.
So-
If you transform, so up there, the 5 and the 7,
Yeah.
somebody types in 7.5 instead of 5.7, it's just time the sum, it's still going to be the same sum.
The sum would be the same,
So
but
the straight sum would not catch transpositions. But then you said something about primeness would catch the,
right, so if you do 5, 7, it's 3 times 5 plus 1 times 7. If you do 7, 5, it's 3 times 7 plus 1 times 5.
Okay.
So this is 22, and this is 27, 26. And I think if you break it out into the cases, you'll find this is different in most cases. That's the 90%. And I think that's happening because 3 and 10 are relatively prime. That's just a hunch. All right. ISBN is similar. So ISBN is a 9-digit code with a check digit, and it uses an algorithm like this. So it adds up the 9 digits, and it multiplies each digit by its location in the code, and then it reduces that sum mod 11. And your digits can be the digits 0 through 9 or the letter X, and then X is treated as a 10. So it's sort of a base 11 set of characters in an ISBN. And I believe this catches all single errors and all transpositions. And this is ISBN 9, it's 9 characters. There's an ISBN 13, which uses more, and there's a lot of variations on these. But all of these just use different facts of modular arithmetic to try to ensure that if it matches the check digit, it's probably a correct code. And these things are all over the place. If you look at a credit card number, it's not just 16 random digits. As soon as you type a number into a website that wants a credit card, it can tell if it's an invalid credit card number without ever talking to a bank, because a lot of combinations of digits are not valid. They have to satisfy certain properties, like this, for example, but different. And you can tell if there's a problem just by looking at certain characteristics of the digits themselves. So this is an idea that finds application in lots of different areas.
Do you know if there's any reason why mod 11 specifically was used?
I believe because there's 11 different characters in the input, but I don't know how that ties in.
Can you talk about, or is it anything you want to talk about, how if you download a piece of software from the internet, there's check digits there to make sure that what you download is the actual code you're supposed to, and
Yeah, exactly the same concept. So things like an MD5 hash, it's an algorithm you can use on typically a binary file, like an executable program that you download. There's a big number next to it, and you can run the thing that you downloaded through a piece of software, and it will tell you what the MD5 hash should be, and you can compare it to what the MD5 hash was supposed to be and make sure that you've actually got an intact file. So here's a sample MD5 hash for 2 files. It says they differ in 6 bits, and you can see there's a number of errors in the MD5 hash for each. Oh, sorry, no, this is something different. So these are 2 hashes that do differ in 6 bits, but they produce the same 128-bit hash. But that's very hard to do. Okay, again, this is mapping the space of, arbitrarily large files down to 128 bits. It's a many to one. There's going to be multiple things that map to this. The trick is, if you're someone writing malicious code, can you write malicious code that still generates the same MD5 hash? And that's really hard to do, supposedly. So the algorithm is usually not involving a lot of complex mathematics. It's a bit of logic operations, some exclusive ORs, and you do a series of these rounds where you basically take your input, break it into chunks, and inside the chunk have these pieces and just perform these different operations. But it's developed by people much more clever than I am, who have confidence that this is a difficult thing to mimic. Right, that you can't take an arbitrary piece of code and tweak it slightly to generate whatever hash you want. You change one bit and you're going to get a wildly different hash. So it's hard to, say, embed malicious code inside something. And it's got magic tables usually of these things. And the code itself, you know, is nothing fancy. It's really just logic operations. But these magic codes are part of it. And this is how a lot of things work. This is how, like, the DES, the old data encryption standard, works. It's just, you know, take these things and swap them and do an exclusive OR, and now flip these two bits around in opposite order and do this 16 times and mix in this magic salt, and here's your encrypted version. But we feel confident it's hard to reverse.
When the people who are doing this do this, do they build some kind of inverse ability into the code that they can do themselves that nobody else knows?
Like a backdoor?
Backdoor, yeah.
That's a good question.
I don't know if it's a good question or not.
It is. It's an excellent question.
I don't know what I'm asking.
It's a question everyone should ask. Yeah, presumably not. But this gets into a bit of a discussion about, like, open standards versus closed standards, right? If you have a group of 10 people behind closed doors creating an encryption algorithm or you know, a hashing algorithm or something like that, and they hand it to you and say, here, use this, how do you know there's not a backdoor in there somewhere, right? If you have an open standard where the code is publicly available and everybody can look at it and analyze it, you probably have more confidence that if there's a backdoor, somebody's going to notice. And this is why, you know, periodically people find vulnerabilities in encryption systems. What did we used to use for routers? Was it WEP? It was either that or WPA, the first one that came out. And people discovered you could crack it in like 5 seconds if you knew how to do it. And so we don't use that anymore for Wi-Fi encryption. But yeah, it's always a good question. And then Google just announced their quantum breakthrough last week. Did anybody see that? So they're claiming that they have achieved a first, which was to be able to solve a problem on a quantum computer that they claim cannot be solved on a traditional computer. And by their estimates, what they did in about 3 minutes on their quantum computer would take 10,000 years on a traditional computer. Although IBM quickly came out and said, well, if you do it this other way, we can solve it in 2.5 days on a traditional computer. And this is always, you know, a back and forth. There's advertising and there's optimism and there's reality somewhere in there. But quantum computing is one of those things that throws all this stuff out the window, because it lets you do a phenomenal number of calculations very quickly, and a lot of this stuff is secure because it's so hard to do all the computations you would need to crack it. 128-bit hash, that's a big number, unless you have 2 to the 128 computers to work on it simultaneously. Then it's a really small number. If you've got a 10-character password, that's really hard to crack, because it's like, if they're just letters, uppercase, that's 26 to the 10th possible passwords. But if you had 26 to the 10th people who could try a different password each all at the same time, it would take you like 5 seconds to figure out what the password was. Everybody tries a different password, one of them is going to get it right, and they just say, hey, here's the password. In quantum computing, the big excitement about it is it lets you do lots of things simultaneously that today we have to do sequentially. So, and the big breakthrough is always like 10 to 20 years down the road, according to the stories you read. It's been that way for at least 30 or 40 years. But sooner or later it's going to happen.
Is that why something called parallel computing, or one of the reasons why it's important today?
Yeah, I mean, that is parallel computing, right? Being able to do multiple things at the same time. And, you know, I've got 4 cores in this laptop. It's basically 4 CPUs that can do 4 different things at the same time. Bigger laptops have 16 cores. There's a machine back in Virginia I do some research on. It's got 28 cores. But the big supercomputers, you know, might have hundreds of thousands of cores. Graphical processing units have thousands of cores on them. With quantum computing, theoretically, you can do much, much bigger numbers than that. And we should talk about quantum computing sometime. That probably fits into a 215 class at this point. Maybe we'll talk about that at the end of the quarter. But it basically lets you have a computer that exists in simultaneous states. And so you can search lots of different branches on your search path. So we'll loop back to that when we get to automata and Turing machines and non-deterministic Turing machines, which are kind of what quantum computers might be.
Can I ask a question about the test?
Sure.
About the midterm exam. I find it relatively easy to work in terms of divisibility.
Mm-hmm.
But congruences are not so intuitive to me.
Okay.
I'm getting used to it because I'm working through some of the problems in that extra book that
I
you
saw.
had. And that works well enough when you say increased practice, increased use,
Mm-hmm.
increases familiarity or memorization or that kind of thing.
Mm-hmm.
If I do a problem on the test or on homework or on the final exam or when I'm out in the middle of the street and I use divisibility instead of congruences. For example, the proof that you just gave up there a minute ago, you proved doing divisibility.
Mm-hmm.
But John, I wasn't here last Friday, and John allowed me to copy his notes before class. And last week, apparently, you proved that same problem, but you didn't go through divisibility. You didn't do it using divisibility. You used it using congruences, and I understood it.
Mm-hmm.
But are you going to have a problem on the test where you say you must do this problem with congruences? You can't do it with divisibility.
I don't think I have one on there, but I'm not positive.
But that's coming on the final exam.
I don't know. So that was somebody, we were talking about that question last week, and somebody had done that for their solution, so they had offered that, and that's why I wrote it down on the notes.
I understood it, and the more I work with it, the better I understand it, the better
Okay.
I know the basic couple little fundamental properties that
Mhm.
you need to do that with, but it's not first nature. It's not.
Right.
It's not immediate for me to think in terms of congruences.
Yeah.
I understand it, but then that doesn't mean I can repeat
Okay.
it.
I don't think I have one on the midterm, but I'm not positive. You can ask me later, I can tell you.
Right.
Someone asked me a question like that last year in one of my CS courses, one of my 222, I think. And I was like, let me check, and I did this to like turn off the screen, and I pulled up the midterm and looked, and I answered the question.
And everybody was looking at the midterm?
Well, no, because they couldn't see it, but I didn't remember that I was recording it, and I posted the recording.
Yeah.
So even though you couldn't see it here, if you went back and watched the recording, people were able to see the whole midterm exam, which nobody told me about until afterwards. So I'm not going to do that this time. All right, let me start talking about crypto. We got 5 minutes here. Let me just introduce cryptography, and probably Wednesday after the midterm, we'll finish up crypto. And then there's no class on Friday because I'm out of town. So that'll set us up to start something new the following week. So what's the idea of cryptography? You have a message and you want to send it to somebody else, right? This is a very old thing to do as long as people have been living apart. You want to send a message to somebody, but you want to do it securely. And so you used to take the message and you'd put it in a sealed envelope and you'd hand it to someone, and they would ride a horse over to the village and they would deliver it. And if anybody tried to take the message, they would kill them. And that works great in theory. It works pretty well in the movies. It doesn't really work so well in practice, because if you run into 50 people, they're going to kill you and steal the envelope. And so physical security has always been a pretty weak way to try to protect information. Trying to say, I'm not going to let anybody see this because I've got it locked up in this safe that nobody can break into. Well, if you can open the safe, somebody else can, right? So physical security is usually a hard way to protect information. So for thousands of years, people have used encryption. They assume that somebody else is going to get physical access to the message, but they code the message so that somebody who looks at it doesn't know what they're seeing. And so that's the basic idea of encryption, and it goes back at least to the Romans, to what we can call a Caesar cipher. So we might have a secret message which says hello, and we have a password, and the password is the number 3, which means I'm going to add 3 to each of these letters. So H is going to become a K, E is going to become an H, L is going to become an O, and O is going to become an R. And so this is what I write on the paper and send with the courier, and 50 people come out and ambush and steal the message, and it says core. Well, I don't know what that means, and so they can't get the secret message. And there's 2 problems with this approach. The first problem is it's pretty easy to crack this thing. For one thing, you can just try subtracting 1, subtract 2, subtract 3, subtract 4. After 26 tries, you're going to find out that all your letters turn into words, and you can probably guess, okay, that must be what the secret password was. If I subtract 3, I get the word hello. And if you've got a big long string of text, it's pretty easy to know when you're turning all this gibberish into something that's readable. So that's the first problem with this, is it's pretty easy to crack. The other problem, which we'll talk about on Wednesday, is this password business. So in order to turn my plain message into an encrypted message, I needed to choose a password like add 3 to each letter. And now I send this with the courier over to the king in the next town, or the queen, and when they get that, they can decrypt it, but only if they also know this password. They've got to know how I encrypted it in order to decrypt it. And so I've traded off trying to keep this message secret for a new problem, which is trying to keep this password secret. That's a little easier, but it's still hard, particularly if I have 20 different people I'm sharing messages with. If I use the same password for all of them, and one of them turns out to be an enemy, that person can now read all of the messages I'm sending to everybody. So I could give each person their own password, but now I've got a housekeeping problem. I've got to somehow say, okay, your password is 3, your password is 17, your password is -6. And how do you do that? And if we try to do that and we try to do commerce on the internet, it would not work, because each one of us, before we could send in our credit card information to Amazon, would have to meet someone from Amazon and say, okay, what's our password going to be? And you don't want to set the password up through email, because email is insecure. And you don't want to do it through the website unless you know that you're actually talking to Amazon, and how would you know that? And so getting this thing going is a problem. You have to somehow get somebody you trust over to the next kingdom, and they go to the queen and they say, okay, the password is 3. And you've got to trust this person and trust that they actually talk to the real person that you're intending the message to go to, and so on. So there's lots of issues with that. So we'll talk about a few of these other, what we call symmetric key ciphers. These things where you have a password that both encrypts and decrypts. And then we'll talk about how we get around that problem with something where we don't need to give everybody the password in order for them to read the message, and also something that's fairly secure, fairly difficult to just guess the password through brute force. And that'll take us to sort of the conclusion of this, which will be looking at an encryption system called RSA, which we still use today. All right, so we'll do the exam Wednesday, and then we'll keep talking about this after the exam.
You're talking about cryptography.